Hi, welcome back to the APES virtual classroom. I'm so glad to see you all here today. Happy Friday. We're going to start by taking a look at the homework that you did with Dr. Sowell yesterday. I'm Ms. Fassler, and I teach at APES at Marshfield High School in Marshfield, Wisconsin. So for our warm-up, we're going to take a look at the population FRQ that you did yesterday. We are, by the end of today, halfway through our review session, so we'll be due for a little bit of celebration. You started yesterday by looking at this diagram, this model of age structure diagrams, sometimes called population pyramids, and you have three countries, X, Y, and Z. And the first thing you had to do is to identify which country had the largest and the smallest growth rate and explain why. So this is a really good example of that common skill that occurs in both of the two FRQ that you're going to write. You're going to use a model to explain an environmental concept and process. So let's dig into this. Which of those countries had the which of those countries had the largest growth rate? You could have said that you needed to say that X had the largest growth rate, but you didn't earn that point until you explained why. And notice, let's look at this third bullet for a second. I can't just say that, oh, country X has the largest growth rate because it's got the broadest base to its pyramid. I have to explain why having a broad base would indicate a rapid population growth. And notice some of the other ways that you could have expressed that. I could talk about the percent of the population being in that pre-reproductive category or cohort. The other point then was for identifying that country Y had the slowest growth rate, and the explanations were sort of the reverse of what we did with country X. Its pre-reproductive cohort is about equal in size to those others, which should be an indicator to us that that growth is slowing. There's not, it's a stable population. We might have even said zero population growth. In the next part of the question, you had to use that model to then explain something else. That's kind of, remember, that big idea of where we're going with this skill. I want to be able to use that model to explain differences in infant mortality rate in this example. So 1 point for saying either that country X had the higher or country Y had the lower infant mortality rate, one or the other, and then 1 point for the explanation. And again, they're kind of opposite of one another. So based on that age structure diagram, country Y is likely an industrialized or more developed country. And I can't just stop there, because if I simply say country Y has lower infant mortality rates because they are industrialized, I just haven't put enough meat on that explanation. My question then is, well, why do industrialized countries have lower infant mortality rates? And I'm guessing most of you honed in on something to do with access to healthcare or better nutrition or better access to safe drinking water. And then on the flip side, country X would have the higher infant mortality rate. It has the age structure diagram typical of a non-industrialized or less developed country, and they tend to have higher infant mortality rates because, or due to, again, the opposite of those reasons. We then had 3 points to really describe a process. I needed to describe the changes that a country goes through as it's going through that demographic transition model that you looked at yesterday. So you needed to make sure that you talked about the changes in birth rates and death rates. You couldn't just describe what was happening in each phase. Really look at that question, and I have to hone in on birth rates and death rates. So initially, birth rates and death rates are both high. In the transition period, birth rates remain high, but death rates start to decline. And in the industrial, or they would have accepted post-industrial phase, both birth and death rates are low. They tend to be, they tend to cancel each other out and both be low. The last 3 points of the question had to do with an incentive that a government could implement to reduce population growth rates. how the government would implement that, and one possible drawback of that solution. So most of you probably went with an incentive or disincentive, an economic incentive or disincentive that the government could offer. For example, the government could offer free access to birth control to limit the size of your family, or the disincentive would be the reverse of that, take away access to birth control for families that had larger families than what the government would have liked them to have. And again, usually that has to do with some type of economic reward or punishment. This was about the only other big strategy that that was listed on the rubric that the government could implement. And then again, you can kind of see the ways that the government would implement that: education programs, incentives for higher education for women, because we know that when women, the higher the level of education, the lower the fertility rate. So lots of different strategies there. And then the potential drawbacks, I think a lot of students probably focused on some of the cultural, social, or religious pushback to try to tell people or mandate the size of their family. Other things like infringement on human rights. Some of these policies are difficult to enforce. Notice that if there are parts of that country, because just because we say that a country is in a certain phase of a demographic transition, think about how large our country is and how we have different regions that vary in their needs. And so a rural area may say, well, we still are largely agrarian and need to have large families. So let's take a look at where we're going today. Now that we've finished unit number 3, we're starting into unit 4. We're going to have 2 lessons on unit 4. And this is another example of a unit where we're really going to dig in to that common theme in both of the FRQs, what we really just introduced in the warm-up, looking at visual representations, models, quantitative data, and using the interpretation of that to then describe and explain environmental processes. When you look at the learning targets in the first part of chapter 4, we're jumping around a little bit in our organization of those. These topics are really just, they don't lend themselves in and of themselves to a lot of experimental design or solutions. So I'll tell you where we're going with our lesson today. We're going to look at plate tectonics and then kind of the atmosphere and how global weather and climate patterns are created. And we're really going to show how reviewing this core knowledge is going to allow us to apply that probably in describing and analyzing larger contextual environmental ideas that we might see on the environmental exam on May 18th. So these questions, these topics in and of themselves are going to integrate really well into a full free response question, where then we start to apply some solutions and experimental design. And you'll see what I mean as we go through the lesson. So let's start off with that first, that geologic idea of Earth, or of Earth systems and how they interact. And we're going to kind of draw from some of those ideas that we've already established. This idea that Earth systems interact, but overall there tends to be this state of balance. And that should sound like a common theme to you when we looked at biogeochemical cycles and the rate at which things move through them. Well, Earth material has to move through a cycle in and of itself. Those same atoms of nitrogen, phosphorus, and carbon are often found in the lithosphere, solid part of our planet. So they're in these short or these long term geologic processes that occur over millions of years are important in helping us really put that idea of biogeochemical cycles all together. And it helps us visualize or get an idea of where we might locate mineral resources or deposits on our planet. And that idea we're going to take into a future unit on mining resources and how we locate minerals that we mine, the techniques that we use to get them out of the ground. And remember that overarching idea that these are non-renewable resources that, because of the span of time it takes to form them, are present on our Earth in a finite amount. Well, and we're also going to look at how these processes have sculpted our amazing planet. And that really ties into that overarching idea of ecosystem diversity. We inherently realize that having a variety of ecosystems is important to biodiversity. Now we're going to look more at the patterns for some of how some of those ecosystems formed. So we're going to do a quick review of the 3 types of plate tectonic boundaries or interactions that can happen at tectonic plate boundaries. And the first of those is a divergent plate boundary. And I'm going to really try and keep it to the kind of core, really big ideas that we need to take away from this, and show you how we could apply that to understanding or describing some larger environmental issue. So at a divergent plate boundary, plates are rifting or tearing apart and being stretched really thin, creating this rift valley. So if you picture some Play-Doh or pie crust or pizza dough, and you stretch it and stretch it and stretch it, and it gets thinner and thinner and thinner as you do that, that's what is creating this rift valley. And I'll show you some actual images, not just the cartoon image, in a second. The other big thing we want to understand about the processes at these divergent plate boundaries is that when I stretch that lithosphere really thin, upwelling of magma, because that's really thin, and there's there's a weakness there because it's been stretched so thin, that upwelling of magma splits that earth crust and pushes those plates apart. And that's what we call seafloor spreading when that happens on oceanic crust. We also create this mid-ocean ridge. So where that seafloor spreads, where that magma starts getting up in the weakening of that crust, it can actually break through and deposit magma, which will cool and solidify, creating these mid-ocean ridges or underwater mountain chains. And finally, a feature that we can predict would be located at a divergent plate boundary are both volcanoes and earthquakes that occur when we have that molten material venting, where the magma is able to rise to the surface. So just understanding how our planet is divided into different lithospheric plates, oceanic and continental crust, really helps us from a human standpoint in predicting where some of these natural disasters can occur and how we can better prepare for those. So here's an image, give you a second to kind of put this in perspective. These are houses or man-made structures here. This is in a hotspot over Iceland where the North American and Eurasian plate are rifting or tearing apart. So this is that rift that's forming. It's one of the few places on the planet that we can see this on the surface of the land, because as we mentioned, a lot of times that's happening on the ocean floor where those mid-ocean ridges form. Here's another image from Iceland as well, showing me a bridge going across that rift that's connecting the two plates, where they're pulling or rifting apart. So that is a divergent plate boundary. Oh, we have one more cool image. This is of the Great Rift Valley, that a lot of us are familiar with that term. This starts kind of in the north up by Jordan, but this goes all the way down through East Africa where the continents are rifting or splitting apart. This is the Great Rift Valley, that thin part of the continental crust as these two plates are rifting or pulling apart. And we've spent a fair amount of time in the Rift Valley on the Masai Mara, on the Serengeti, looking at some of the amazing biodiversity that results from the diverse ecosystems created by tectonic plate activity. Okay, so the next type of tectonic plate boundary is convergent. This is where two plates come together. I'm going to give you just about 30 seconds to familiarize yourself with this diagram. There's kind of a lot going on here, and see if you can recall the processes that are occurring, if you could describe the process that's occurring at a convergent plate boundary, and how that leads to the certain geologic features that we see there. So take just about 30 seconds and look at that and see if you can answer those. Well, I'm going to give you a little hint, and it's one of the key vocabulary terms that I want to have in my repertoire if I'm going to explain what's happening at a convergent plate boundary. Remember, where those plates come together, one plate is going to subduct or push underneath the other plate. When that plate subducts, when it pushes underneath this other plate, if this is oceanic crust that's pushing underneath here, when that happens, this oceanic crust is pushed down into the mantle, and that solid earth material melts and becomes magma that can be vented to the surface. Then I can have volcanic eruptions that bring that molten melted material to the surface and deposit it, creating what we call a volcanic island arc. The collision of these plates can also cause earthquakes. The third type of plate boundary is a transform boundary or a transform fault boundary. This is where we have plates grinding past one another in opposite directions, like we see on the coast of California, where I have the North American plate moving one direction and the Pacific plate moving in opposite direction. And that creates friction that over time will be released as an earthquake. So earthquakes are very common because of that buildup of pressure. This is sort of that overview then of all of our planet broken down into its different tectonic plate boundaries. And let's just make sure we can make sense of this based on that review that we just did. So see if you can find on here, well, you can see this, this is a good example of a spreading zone. And remember, at a spreading zone, at a divergent plate boundary, the main feature I see are those mid-ocean ridges. So this is the mid-Atlantic ridge where those plates diverge, molten material comes up at that seafloor spreading center and is solidified. Well, one of the key things we said happened at a subduction zone were those island arc volcanoes. And notice this, we've got this big belt of where two plates are coming together and one is subducting under the other. So there I have those island arcs. You may have talked about the ring of fire, this ring of intense volcanic and earthquake activity along the rim of the Pacific plate, this huge subduction zone, and that just, it kind of dissects the entire planet in two. So let's do a quick check for understanding and see if you can describe and explain, and the kind of relating this back to the bigger picture. So remember that these geologic processes have sculpted our planet over time. That's created a lot of ecosystem diversity. When that plate subducted into the mantle, I was recycling earth material. The same atoms that make the same elements that go together to form minerals are constantly being recycled. They're solid and get melted into magma that then comes up on the seafloor and creates a ridge, or is vented through a volcano and creates an island. It just happens over a time span of millions of years. And it's always a really challenging thing for science teachers to try to help our students visualize what that long time frame is going to look like, how long those processes take to happen. Remember, this is going to help us know where valuable mineral resources are located, where I have tectonic plate activity, and I can have minerals from the mantle of the earth be deposited on the surface. Those processes help me predict that location. Because these processes happen not on a human time scale, but a geologic time scale, these mineral resources are present in a finite amount. They are non-renewable. And oftentimes the location of those resources, there's no link between like which countries are the most populous or industrialized. Do they have all the minerals? Obviously, the processes that deposit these minerals don't take into account geopolitical boundaries. So countries that have a lot of these resources have a lot of power if they're valuable resources. And there brings in a lot of the environmental science aspect by looking at that and how humans interact with their environment. So let's do a quick check on some of those concepts before we move on to the atmosphere, because we're going to kind of switch gears and go to a new topic here in a second. So this should look familiar to you. It's showing me the Earth's major crustal plates. Just a quick identify the letter, area where new crust is being created at a divergent boundary. That's letter B. That's that mid-Atlantic ridge we just went over. The location of an island arc formed by subduction. I think my students may have seen this question. You may have as well. And I think they're like, wow, there's only one place that kind of shows islands there. So I have a pretty good chance that that's letter E. Here's another multiple choice question. Scientists are looking at new locations to generate electricity using geothermal energy. Which of the following locations would be the best choice for a geothermal generating plant? So again, here's where you're going to see a little more application of the content that we're reviewing. Remember, Iceland has a lot of geothermal energy. We saw those rips where the tectonic plates are moving apart, and a lot of geothermal activity and thus geothermal energy there. Now let's go a little one step further, and this is where we're going to see if we can describe and then explain. So Japan, Indonesia, and the Philippines are examples of volcanic island chains that formed along subduction zones in the Western Pacific. This is the ring of fire we just looked at. Describe what happens when two plates collide along a subduction zone. Remember, one plate pushes underneath the other. They already gave us that term subduction, but I could have used that in my description again. And then I want to explain how this subduction leads to volcanic activity. So remember, when that plate subducts, it goes into the mantle, it melts, and then that is molten material that can rise to the surface or be vented through that volcanic activity. So now we're going to go on to sort of the second half of the lesson for today. We're going to leave the lithosphere and the solid part of the Earth and go to the atmosphere. So quick review on this first learning target is just really kind of what the atmosphere is all about, sort of some of these facts that we need to remember about it. And then we're going to look at how understanding the basic working of the atmosphere will allow us to, guess what, explain some other kind of process. So we have lots of different layers, but I think we really want to focus on the troposphere and stratosphere. When you remind yourself what happens in these different layers, mostly from the air pollution unit, this is really where humans are interacting with the atmosphere. Boy, it seems like there's a lot going on in this graph, so let's kind of break it down. Oh, we have to remember the composition of the atmosphere. That's another essential knowledge statement. And we reviewed that when we did the nitrogen cycle, because remember, the atmosphere is a major sink for nitrogen. And I now am connecting that because there is so much nitrogen as a gas in the atmosphere, nitrogen cycles really quickly. Unlike phosphorus, that does not have a gaseous phase. I don't have any phosphorus gas in the atmosphere. Now, what else is this graph showing me? Okay, I got all kinds of axes labels here. My y-axis is temperature. I have another y-axis up here. This is my atmospheric pressure in millibars, and my x-axis is temperature and atmospheric pressure in millibars. It looks like there might be two different labels on my y-axis. They're both altitude, they're just in different units. One is in miles and one is in kilometers. So I really want you to focus on just this little part of what's going on this line down here. And let's just do a quick interpretation, because it's this part of the atmosphere that we're going to live in for the rest of our lesson and try to explain what's going on there. So let's do miles. Maybe that's something you can visualize pretty easily. Whoa, I have to go up pretty far in the troposphere before I even get to the stratosphere. Remember, Denver's the mile high city. That's 5,280 feet. That's only 1 mile. So let's say that I'm hiking some 14ers in Colorado. They have a lot of 14,000-foot peaks. When I'm climbing a 14,000-foot mountain, I'm about 2.5 miles above sea level. So what I really want to focus on is the fact that as I increase in altitude, as I go from sea level up to the top of a mountain, the temperature decreases. It gets colder. So hold that thought. As I go from sea level up to the top of the mountain and increase altitude, I decrease temperature. That's really what we want to focus on. It's the essential knowledge that we're going to have to use to explain and describe other processes. Well, let's see what those other processes are. Global wind patterns. We're now moving in to this idea of how weather and climate patterns are created, and that I can apply to explaining a really big issue in environmental science, a really big concept. So boy, it seems like there's a lot going on here as well. We have sunlight striking the surface of the earth and it's being heated. And although there's all these different arrows, let's just kind of focus in on this one little part of the graph. And everything else is just repeating. There's just a pattern that's happening here. And in your textbook, you may see diagrams like this that show you more complexity, maybe more labels as to the type of air masses. Just don't even go down all those little facts. We want to be able to describe and explain a big concept. So that's where we really want to dig in here. Don't get too deep in the weeds on a lot of those facts. Not that they're not important, but because we're reviewing and we know what we're going to be asked to do, I'm really focusing in on the describing and explaining. So sunlight strikes the surface of the earth and it heats the surface of the earth. And that air mass, as it's warm, it's got a lot of space between the molecules. So at the surface of the earth, that air mass, as those molecules of air get heated, when I use the term air mass, think about it like a big block of air. That's what I want you to visualize. So as the surface of the earth is heated, that big block of air right over the surface of the earth is heated. And when I heat up the air mass, that big box of air, those air molecules move further apart. They spread out and they become less dense. There is a very small mass of air molecules in the same volume. Well, remember what I told you to carry forward from that complex temperature altitude graph that we just looked at? As that air mass, because it's warm and less dense, those molecules are really far apart, that less dense air mass is going to start to rise. Well, what happens when we go from sea level to the top of the mountain? It gets colder. And as that air mass, as that box of air cools, those molecules start losing their kinetic energy and they move really close together and become a lot more dense. And as they become more dense, then they're going to fall or sink or descend. Well, what do I create when I have air masses that warm, become less dense, rise, and then they cool, become more dense and sink? I create global wind patterns. And that you need to be able to just describe that process, not a lot of nitty gritty about the names of all those different air masses. So let's dig a little bit deeper then into this idea of global wind patterns. So hopefully you're pretty good with this rising and sinking of air mass creating wind patterns. These wind patterns, you might remember, are big conveyor belts to transfer heat, but they also transfer moisture. What do I have when I have temperature and precipitation? I have climate patterns, and climate patterns determine patterns of biome distribution. So this is what I'm getting at. In the big scheme of things, I'm going to have to be able to describe and explain these processes so I can then relate it and step back and relate it to a broader environmental issue. So we're getting into reviewing enough content that we're really starting to connect a lot of these different topics into a very rich description and explanation. So let's go back to our little model of this warm air mass with low density. Well, picture a little water molecule in there. When I have a low density warm air mass, there's all kinds of space between those water molecules, between those air molecules for little water molecules to slip in. It doesn't work quite that way with a cold air mass where the molecules are really close together and very dense. There's just not room for those little water vapor molecules to slip in there. So now we want to relate not only temperature and altitude, but what happens also to that air mass as it's rising and cooling, and the air mass gets more dense and it can't hold as much water. Now we're relating this to the hydrologic cycle. As that warm air mass that can hold all kinds of water rises and cools, it can't hold as much precipitation. We get condensation, or as much moisture, we get condensation, and all that moisture falls as precipitation. So if I look at this graph, I can see that there is a direct relationship between temperature and the moisture holding capacity. The warmer the air mass is, a little flame there, the warmer the air mass is, the more moisture it can hold. So at the surface, when that air mass is really warm, it can hold a lot of moisture, but as it rises and becomes more dense, it can't hold as much water vapor, and that falls as precipitation. So I'm creating wind patterns, but I'm also creating patterns in precipitation by the movement of these air masses as well. So let's see if we can take a step back for a minute and go back to how that surface got heated to begin with, and why isn't every place on the earth the same then? If we always have the surface of the earth heating an air mass, and that air mass rising and letting go of its moisture, and we create those patterns or bands, why don't we just have the same pattern or band all over the planet? And that's where we need to review this concept of solar insolation. Remember, that stands for incoming solar radiation. And that when I taught this to my students, the way I explained it, and that's what this diagram's kind of showing down here, is that if our Earth were a cube, we wouldn't have to talk about solar insolation, because the sun would always be striking the Earth at the same angle, whether it was the North Pole, the equator, or the South Pole. I'd have the same amount of incoming solar radiation. But obviously our planet is not a cube, it's this beautiful sphere. So as I curve up to the North Pole, let me get my curvature to the North Pole here, when I have that sunlight coming in from solar radiation from the sun, it's not striking straight on. At the equator, and remember this is 0 degrees latitude, I can have 90 degrees north or 90 degrees south. When I move from the equator, 0 degrees latitude, and I get the curvature of the Earth, that sunlight is striking at an oblique angle. And so the same amount of solar energy at the equator is spread over a pretty concentrated small surface area, but because it's striking at a curvature and that sunlight has to come in and hit at that angle, the same amount of energy is spread over a much larger surface area as I move toward the pole. So that's starting to make a connection to me between where biomes are located and the climate that it has. Let's do a little guided practice on this quick. So here's a beautiful NASA image that shows me the Earth with a unit of net radiation represented in different colors across this continuum. And my unit here is watts per meter squared. So in other words, how much energy per square meter of Earth's surface. And I can see, well, I'll let you decide how you're going to say that. Describe the relationship between latitude and radiation per unit area. And Next, I want you to be able to explain the pattern. Remember, we're really focusing on describe, explain using some type of model. So once you've simply, the easier part is maybe describing what happens, that identify, interpret, that Dr. Sowell and I have been working on with you. Next, you have to be able to explain solar insolation. So the relationship is there is an increased amount of solar radiation at 0 degrees latitude, or the greatest amount at 0 degrees, and that it decreases as you increase latitude. You need to be a little bit careful here because it's said to describe the relationship between latitude and radiation per unit area. I need to make sure that I'm explicit, that I understand. If I simply say the equator and the pole, I really haven't tied in that idea of latitude. So I need to know that the equator is 0 latitude. I could simply say that as I increase latitude, I decrease the solar energy per unit area. That's basically what I said here. Just make sure that you get that the equator is 0 degrees and the North and South Pole are each 90 degrees. And I have that pattern repeat as I move away from the equator. Explaining that process is solar insolation. The amount of solar radiation that hits the equator directly, all that energy is absorbed over a small area. And at high latitudes, that same amount of energy is spread out over a larger unit area. That's why it's important that we look at our unit, the amount of energy per unit area. So we're going to now go one step further. Now that we understand this idea of how winds are created and how winds transfer both heat and moisture, and that varies because different amounts of different places on the surface of the earth get different amounts of incoming solar radiation. So we tie that all together. Now we want to take a look at how that all relates to the seasons on the earth. So I'm going to show you a quick video clip that explains it, and then we'll look at that still image and walk through what's happening.
Earth remains tilted in the same direction all year round as we orbit the sun. But that means the sun's light shines differently on Earth at different times of the year. Let's look at Earth when it's winter in the northern hemisphere. Observe how the North Pole tips away from the sun. This means that sunlight strikes the northern hemisphere at a shallow angle for a short period of time. This is why winter weather is generally cool, with short days and long nights. As Earth orbits the sun, we move towards spring in the northern hemisphere. Now Earth is tilted neither toward nor away from the sun, as day and night are about equal in length. As we make our way to the summer months, notice that Earth is still tilted in the same direction, only now on the other side of our orbit. The North Pole is tipping toward the sun. Sunlight strikes the northern hemisphere more directly, and the sun stays in the sky for a longer time. Compared to winter, summer days are warmer, and the sun stays in the sky much longer. Notice too that while it's summer in the northern hemisphere, it's winter in the southern hemisphere. Because of Earth's tilt, the seasons aren't reversed. We observed how Earth's tilt creates the different seasons throughout the year. How does this affect life? Plant life and other photosynthesizers, we call them primary producers, depend on sunlight. They respond to the changes in the seasons. Earth-orbiting satellites measure the amount of carbon dioxide absorbed by these primary producers. Bright regions on this map show where they devour the most carbon dioxide, turning light from the sun into oxygen and natural sugars. In spring, when sunshine strikes the cold waters of the North Pacific, productivity skyrockets. Phytoplankton and other microscopic photosynthesizers form the base of the ocean food web, and all ocean life responds to changes in the seasons. On land, forests grow green during the spring, brightening the continents. During winter, continents in this view turn dark from a lack of photosynthesis.
Oh, what a beautiful job in kind of bringing together a lot of those ideas. I think we maybe looked at an image in when we reviewed the carbon cycle about changes in carbon dioxide concentration from northern hemisphere to southern hemisphere in different seasons. Now we can explain why that is. We're really starting to connect different ideas, and that's often what they want us to do in our free response is draw and bring together a lot of different concepts. So here's the simple static cartoon diagram that again shows me, you could see it in the animation very nicely, the areas that are getting the greatest amount of sun and the areas that are shaded. So remember that during the summer, when the southern hemisphere is during our summer in the northern hemisphere, when the southern hemisphere is tipped away, the South Pole could have almost 24 hours of darkness. The sun may never quite get over the horizon, but just the reverse is true later. Now the northern hemisphere, excuse me, the North Pole is up in almost complete darkness, and the southern hemisphere has almost 24 hours of daylight. So the last big idea we want to take a look at is how the oceans influence climate by absorbing different amounts of solar radiation. And I'm just going to present the big idea of ocean circulation, and Dr. Sowell's really going to apply some of this little bit of content that we review here. So let's take a look at how oceans influence climate by absorbing solar radiation and releasing heat, another piece of the puzzle of global circulation.
Earth is the water planet. Although 40% of Earth's population lives within or near coastal regions, the ocean impacts people everywhere. Most of Earth's water is stored in the ocean, a driving force for weather and climate. The Earth's surface is warmed unevenly by the sun. Heat, a form of energy, helps drive ocean and atmospheric circulation. The ocean absorbs and stores more heat than the atmosphere. Both the atmosphere and ocean move heat. The atmosphere does this quickly, the ocean slowly. At the ocean's surface, winds drive currents. Multiple forces keep the global ocean conveyor belt, or thermohaline circulation, in perpetual motion. Below the surface, deeper current.
We're not going to go into the deep currents, but hopefully that was a good review for you about the idea that oceans and the atmosphere can both absorb heat. Water has a very high heat capacity. When heated, it tends to really hold on to that heat. So we have heat and moisture being transferred by atmospheric currents. We have heat being transferred by ocean currents, and you're going to pick up with that idea tomorrow or the next on Monday in the next lecture with Dr. Sowell. So let's go back. We have one other aspect of weather and climate that we need to take a look at, and it's how the Earth's geography influences that. So I'm going to just ask you to quickly recall what we went over about how when an air mass rises and it gets cooler, it loses its water vapor capacity, condensation occurs, and that falls as precipitation. That description of that process helps me explain the rain shadow effect. And it helps me really understand another aspect of how different climate patterns are distributed around our planet. So here's a simple cartoon image of the rain shadow effect, but I think we're at the point where we can look at this in a little bit broader, more realistic context. So here's a beautiful physical map of the state of Washington. Just as a reminder, this is Puget Sound. We're up here in the Pacific Northwest, in the very northern corner of the United States, and I have the Cascade Mountains there. So I want to see if you can visualize based on the cartoon image that we just looked at, what's happening here. So I have these prevailing winds that bring this moist air mass in from the Pacific Ocean. And as that air mass rises to go over the Cascade Mountains, it cools, it loses its ability to hold water. You don't even have to quite go that far. You can just say the air mass rises, cools, and drops the rain as precipitation. It can't hold as much water. And then on this side, you may have learned this as the windward and leeward side of the mountains. Notice that I've got a very different, I can tell by looking at the map here that I have a very different ecosystem. That looks like there's a lot of vegetation here. This looks like there's almost no vegetation. Well, let's relate that to a map that shows me annual precipitation in the state of Washington. You probably realize that Seattle is famed for the large amount of precipitation it gets. Look at in these areas where the greatest amounts of precipitation, even in this like hot pink region, I have 100 to 140 inches of rain per year. When you're done here, go and check in your local area how much rain you get per year. Obviously, some of you live in this region, but just as a comparison so that you have an idea of how to compare it to how much rain you get. That's a lot of rainfall. But now look over here in that area on the leeward side of the mountain. Here's my Cascade Mountains where all that air mass is rising, dropping precipitation, and then continuing on down the other side of the mountain. Look at the dramatic difference. I went from 150 inches of rain a year to less than 10 inches of rain a year in really not that long geographic distance from point A to point B. So the rain shadow effect helps me the understanding the geography of a region helps me explain a lot about its climate as well. Here's another really good example, just a little bit further south of Washington along the Pacific Ocean. Here are the Sierra Nevada mountains in California, the San Joaquin Valley, where a lot of our food is grown. And then look at on the other side of this, I have all these this forested range in this area. And then on the other side of that, I have the Mojave Desert and Death Valley. So geography, the location of mountains has a big influence on climate and weather patterns. So let's do a quick check for understanding of the couple of the concepts that we went through in the second half of the lesson, where we looked at atmosphere and how that creates weather and climate patterns. Which of the following causes the air to rise into the atmosphere in the areas labeled A, B, and C on the diagram? And the correct answer is C, warm, moist air that is less dense than the surrounding air. Remember when we looked at that first image that looked kind of like this, I just focused in on one area where that was happening. Remember this, we're seeing patterns here to this process. And that is what is determining the location of biomes. Why do I have tropical rainforest at the equator? Because I'm constantly circulating in that warm air and dumping that precipitation on a daily basis. If you chose letter B, which may have been one of the most selected incorrect answers, this is something we're going to address in a little more detail later. We have, guess what, another model that I'm looking at that's showing me some data that I have to use that model or representation to describe or explain a process. So I have the relative solar energy at two different locations throughout the year. Let's make sense of our graph. I show the months from January to December. So I'm looking at change in seasons. And the relative amount of solar energy, that incoming solar radiation or solar insolation, I can see that location 1 tends to have about a flat line. There doesn't seem to be a whole lot of difference in the amount of incoming solar radiation throughout the year. And location 2 has a very dramatic change in the amount of solar radiation. and it looks like I have seasons of the year where there are times that when there's a small amount and times where there's a peak amount of solar radiation. So take a look at that multiple choice question. Which of the following can be concluded about the latitudes of the two locations? And hopefully you picked letter B as the correct answer. Location 1 is closest to the equator. I know that location 2 is most likely the northern hemisphere because it's during the northern hemisphere months of June, July, and August that we are tilted towards the sun and would be experiencing the greatest amount of incoming solar radiation. We have a little bit of guided practice. Whoa, looking at another diagram, go figure. So here I have the ocean, here I have city A, here I have city B. Identify the city that receives the greatest amount of precipitation. So this is easy. You don't have to explain anything yet. Want to be a little careful. I guess they could give us a diagram where I had a wind coming in from the other direction. It seems like all the rain shadow effect diagrams that we look at kind of have that wind going from left to right or from west to east. So I have to be a little bit careful there. Obviously, the greatest precipitation is going to be city A. And the explanation for that is that air mass that blows in off the ocean has a lot of moisture, has a lot of water. As the air mass rises to ascend or go over the mountains, it cools and the water falls as precipitation. It's really the greatest amount of detail that I need to provide there. So just a quick debrief and summary. Why do we care? Remember that in the big scheme of things, understanding how solar radiation strikes the surface of the earth, how air masses are heated, creating wind patterns that transfer heat and moisture, and that the ocean can hold a lot of heat and transfer that heat. All of this helps us explain patterns of biomes, which are really different kinds of ecosystems, that ecosystem diversity. Just so that you make sure and see all the essential knowledge statements from the second half of the lesson on the atmosphere. These are the first things that we looked at when we looked at gases in the atmosphere and the relationship between temperature and altitude. We looked at how global winds are created and those patterns. And then we have all of these essential knowledge statements that really dig into this solar insolation and the tilt of the earth and different seasons. So in terms of AP exam practice, this is no homework Friday. Woo! Dr. Sowell and I feel like you guys have been working so hard. We're halfway through the content. You've really been digging in and practicing a lot of FRQs. And like I said, there's not a super good experimental design or solutions that relate directly to this content, but we're going to use all of this content in the next couple of lessons. So don't worry, you'll come back and get some more FRQ practice homework. That being said, I would like why doesn't everybody try to get outside this weekend? I know that it's hard. We know that this is hard for you reviewing for AP exams kind of on your own. We're here for you. We hope that you're getting a lot out of your virtual lessons. We wish we could answer questions for you, but just take a step back this weekend and get outside, spend some time with your family if you're not too sick of them yet. Maybe go pick up some litter by yourself somewhere, but then maybe on Sunday evening, just come back and say, okay, I'm gonna take a couple minutes to review what we went through in those first 3 units and halfway through number 4, and then we'll see you next week. So have a great rest of your day. Thanks for watching. Make good choices. See you next time, guys. Hola.